So one thing I did do is I put up the z-score calculation, and again, you're going to want to have this memorized, and you're going to see it enough where you probably will before the end of the semester. Okay, so we are trying to figure out basically if we've got a normal distribution of money that's spent in this town, and we put ourselves, it turns out we live about right here, but let's just say we just randomly put our spending. This is $750. And we want to find out what's the likelihood that someone spent more than us, meaning they spent more than $750, which is that area of the tail right there. And we want to figure out what that area is. This is the answer to our question. Let's put a question mark. Okay, so we want to figure out, first of all, what's the z-score for that? And then we can do a normal CDF calculation. So we've got the value we spent, 750. We've got the mean is 500. We've got the standard deviation is 238. And we can get our z-score. It's about 1.05. I forget what it rounds to. But basically, we're going to go from a z-score of 1.05 to, well, positive infinity, whatever number you want to put there for a really big z-score. And when you plug this into a normal CDF calculation, and if you have to do it by hand, it's going to be normal CDF with your lower bound, 1.05, your upper bound, 99, 0 and 1, always keep those the same, and you get approximately that answer right there. Okay, so what we get to skip today is going over inverse norm, but it's important to remember that if you know the percentile, or actually one of the key things is if you don't know one of those values, if they tell you, ask you to solve for the mean or for the standard deviation or to solve for the x value, then in any one of those three cases, you're going to have to use inverse norm to, first of all, figure out what your z-score is. All right, that's what we learned on Friday. Okay, the purpose of this is that there will be problems, and all right, and if you did get a different answer, then we can look at that one later. Maybe we can come back to it, see if something is up with that. There will be problems almost certainly on your AP test, and you'll see them in class too, where you're given a histogram and they want you to estimate the standard deviation. And one of the things we learned is that the standard deviation, the first standard deviation, is going to be at what we call the inflection point of this curve. And there's going to be one right here, one right here. Here's the mean. So I can just roughly estimate what the standard deviation of this is going to be based on that information. So if my mean here is approximately 30, then my first standard deviation is going to be about 10 away, maybe at 40. Here's 20. So my standard deviation for this one is going to be approximately 10. And with a question like this, they're not asking you to get more specific than that. Now with this one, the mean is going to be 0, and the first standard deviation looks to be about 1 away. All right, so it looks like our standard deviation here is about 1. Oops, why did I do that? Let me try and write that the correct way. Standard deviation is about 1. Because you can see right here, this comes down to 1 right there. So that's the idea behind these two graphs. So we can get a rough approximation just by a graph. We did talk about that a little bit, so it's worth bringing it up. Let's look at this. We are actually not looking at inverse norm today because we did that, but we do want to I want to review just a little bit which function to use and why. I kind of already did, so I don't need to say much there. Then we're going to be looking at the last little bit from chapter 6 in your book. That's what this is all about. So hopefully you read this, but there's just a little bit more dealing with, let's see. Oh, random notes. So there's a little bit more related to the normal distribution that we need to talk about. Okay, this is actually something important here. Let me see. Okay, let me go back. All right, so I just wanted to bring everything up. So the progress checks that I mentioned to you guys, and some of you already went through and started doing them, those are actual assignments that you must do in order to, and you'll get credit for doing it. But luckily, and there's a lot on this page, so I want to point out some of the highlights. I don't grade those progress checks for correctness. All I'm going to do is I'm going to go and make sure that you actually did them. And they aren't due until the end of this quarter. So honestly, if you wanted to wait until the very end, and you're going to get, I think, like 4 or 5 different units worth of progress checks assigned to you. And if you want to wait till the very end, you can, though I don't recommend it. What I recommend you do is I'm going to assign these along the way as we go through these units. And it's going to be good for you to kind of use them as review for your test. Okay, so those progress checks are hopefully very helpful to get you understanding what you need for the test. The AP progress check for Unit 1 is, there's actually part of the second test is going to be really useful for preparing for this test tomorrow. So another note right here, when we're looking at AP units, they have 9 units, but we have 12. So our numbers don't align. It's not like you say, oh, this is Unit 5 in class, I'm going to go Unit 5 for AP. It doesn't work quite that way. So there is a little bit, but I'm going to try and communicate. If I'm saying, hey, do AP Unit 4, then I always label it as an AP unit. So I'm sorry it doesn't line up perfectly, but I wanted to go over to Canvas real quick.
Hey, real quick, Mr. Davis.
Yes.
Did you say test tomorrow?
Yeah, test tomorrow. Cool. And remember, we got tests coming up like 1 a week, so it's just going to be that way. Anyways, so here's something that you guys need to be aware of. I'm going to put this into student view. How you turn this in. Yes, I do. Okay. Sorry about this. You're going to have to go to AP Classroom and do the progress check. And hopefully a lot of you already were doing that. But what the heck? I'm in the wrong course. Sorry about this. All right. It's just a bit of a mess. In statistics, I'm recording this too. This is going to be awesome. I recommend everyone come back and watch this later. Okay, now we're in the right course. I'm going to be a student here, so it looks the same for you guys. Here it is. Sorry about that. There's this new module. It's AP Progress Check Semester 1. These are assignments that are going to be posted that you have to do. But here's all you have to do. Once you've gone to AP Classroom and you've done the 2 progress checks, all you need to do, I need to change that. It's not due September 8th. But you just need to come here. You need to just type in done or whatever you want and submit it. And all that does is it tells me in Canvas really quickly that you did it. And then later I'll go back. It might be later in the semester when I go back to confirm that you actually took all those tests. But hopefully that makes sense. If you have questions on how to do that, make sure to let me know. But you're going to see more progress checks assigned there. So just keep that in mind. Okay, I'm going to skip past all the inverse norm. Come back to this. Okay, so which function to use? No, I didn't want to do that yet, sorry. We already talked about this, but just as a reminder, if you are missing the anything on the right side, the X value, the mean, or the standard deviation, then you're gonna have to solve for that. You need to use inverse norm. But if you already have everything on the right side, then you're basically just solving for the percentile rank. And there you're gonna, basically that's the same as the area under the curve. And that's gonna be your normal CDF. Okay. This might be a useful thing to come back to, but anyways, we're gonna go to Desmos again. Put that in the, oops, I'm gonna send that to everyone. All right. Make sure you navigate your way there. And the class code for today is right here. I'll put that in the chat as well. Okay. Thanks for letting me know that. Okay, so I will let everyone navigate over there, and you can skip slides 1 and 2 and just go straight to 3 and wait on everyone there. So we're going to be learning the last little bit about normal distributions today and just some ideas about them that we need to understand. And we're going to be talking about transforming the data. So what happens to the mean and standard deviation when we add or multiply all the data values by the same number? So we're going to start with just adding and subtracting. So here, the data set is basically thousands of dollars that people earn at this particular company. So you got 29,000, 32,000, and so on up to 185,000. Okay, so that's the main idea right here. And I'm going ahead and moving to slide 4 at this point. Okay, now there's nothing to do on slide 4 except this slider on the left. So you should be able to click and drag it. So anyone coming in, you can just go to slide 4 of this, and that's where we're sitting. So before we do anything with this slider, and you might already be playing with it, but that's okay. Notice we have some red values and some black values in the middle. So median, mean, and mode are shown right there. The standard deviation is given as well, and the IQR, all that fun stuff, the range. So what we want to do when we slide K, notice it says that when we, this is representing everyone getting a $6,000 raise. So I'm going to go ahead and just slide this over, and you can do it quickly, you can do it slowly. But as you do this, you see what happens. All right, so if you are looking at your own screen, you can just slide that back and forth to at your leisure. And what I want you to do, after you've kind of visually seen what's happened with those dots, I want you to now pay attention to those red values and the black values as you slide it. Okay. So I'm sliding it back and forth. Anyone who's not on the looking at their own, and if anyone's just looking at the Zoom call, you don't have to be. But if you happen to be looking at the Zoom call, you can see what's going on as I slide it back and forth. So some values change, some values don't. Okay. So what I want to do before we just talk about this, I want you guys to try and basically assess what happened here. So if you go to slide 5, you've got a couple of questions, and you can answer those real quick. Okay, so pretty much everyone's had a chance to answer. The mean, yeah, if you went back and slid it over and over again just to double check, the mean increased. That is an actual data point that comes from the data. Well, how do I say it? That is kind of a measure of position. Okay, so that measure of position, the mean, the median, the mode, any individual data point, the first and third quartile, the max, the min, those are all different points of position in the data. And so they're all shifted up by 6,000. Okay, the range, on the other hand, is relative. It is a measure of the spread of the data. And so if everything moved up together, then the spread hasn't changed at all. It stayed the same. And finally, the shape of the dot plot also didn't move. It did move up, but it didn't, the shape of it didn't change. So if you think back to geometry, this would be like just a translation, like a literal translation where you take this and you slide it over, and you know that, okay, I don't need to go into that analogy any further, but that's the main idea. Okay, so I'm looking, a lot of you are already on slide 6, and that's fine. So we can see what happens. Center will move by a constant amount when you're adding and subtracting. The spread and the shape remain the same. So now we're going to look at multiplying and dividing every data value by a constant. Same thing on slide 7. Okay, so slide 7, not a whole lot. I mean, it is exactly the same. So there's no difference, except now rather than getting a $6,000 raise, now we're going to double everyone's salary. So everyone's salary gets multiplied by 2. And as we slide this, you can do this. Now you know what kinds of questions to expect. You can see what happens to the shape, you can see what happens to the data points themselves, and you can see what happens to the values. So slide it a few times, pay attention to the mean, median, and mode, how they change, and then pay attention to those red values, all the measures of spread. All right. So I will leave it there for a little bit. Okay, I'm going to go ahead and move forward. You guys have a few more questions related to this. So what happens to your measured center, your spread, and your shape of your data when we multiply by a constant value? Okay, so you guys did a great job. The measures of center multiplied or divided by that constant. So did the measures of spread. So those measures of spread are affected by multiplying and dividing by constants. The shape of the data, what it did is it compressed or stretched the distribution, but it didn't change it any other way. All right, so it doesn't completely change the shape of it. All right, I'm going to, all right, now you're on slide 9, probably. And what I want you guys to do is go ahead, give that one a shot. I'm just gonna pause here. You guys can take a little time to try and answer what's on slide 9. Most of you did really well on this. So if you're looking at it, you should have noticed, remember your IQR is basically the box in the middle. Where's your Q1, which is gonna be, from my vantage point, it looks like it's at about 17 and a half, 18. If I project this line down, I could tell myself that the Q1 is approximately 17.5 cents, but you might say 18, it doesn't really matter. We're just approximating here. Now Q3 is at the top of the box, not the max, but the box itself. If I project that down, I'm gonna say that's right at 25. So Q3, I'm gonna project that right at 25. The median seems to be around 21, 22. I'm gonna say 21 for the median. But again, if you're within, one or, if you're close to that, that's good. So the median, I'll put 21. IQR is going to be 25. I'm just going to go with 18 so it stays whole numbers. So 25 minus 18 will give me 7 for the IQR. Okay, now for the bottom part, it wants to find out we have a federal tax that's 18 cents that's added on top of whatever the state tax is. And this is constant for every state. So what are the approximate ranges? What's the value of the median and interquartile range? The median, because it's a measure of center, we add to that. So we just learned that we'll take the 18 cents and add it to our median. So if we had a median of 21, we have to add the 18. So our new median is going to be about 39 cents per gallon. And then the interquartile range is not affected by adding a constant. So it's going to stay approximately 7. They say 7.5. So those are the two answers we're looking for. Median of 39 cents, IQR of 7.5 cents. Okay. I'm going to skip slide 10. And then 11 and 12 we're just going to talk about really quick. So this is the idea of exponential growth that they're showing here in slide 11. And at this point, you don't need to be in your own Desmos anymore. You can just come back to the Zoom. We're not going to do any more activities with it. So if we are looking at the exponential growth, you can kind of see what's going on. Well, the problem is, and this is a question, this particular lesson, all these kind of have a little bit of like real world implications about it. So why is wealth inequality increasing? Well, notice that all of these are still going up. So if I kind of drew the exponential curve to model what's going on, all these are going up. Now this is kind of a baseline because there was really no wealth to begin with. So we're looking at the bottom 90% right here, the top 10% right here, and then the top 1% right here. So anyways, what we've got is very little wealth that existed for the bottom 90%. So there's even if it grows exponentially at the same rate, which about, I think they said like 5%, I forget, let me go back the slide, is about, 4%, I'm sorry. So even if everyone's going up at 4%, if you have less to begin with, then it's not going to grow nearly the same rate as what 4% growth of billions of dollars or even millions of dollars would be. So there we go. In the top 10%, you know, you can see some appreciable growth there. So there's definitely the separation. So as you go along, the actual gap between gets wider. And we can see that even if everyone's benefiting, we're not benefiting equally. And that's just, it's just baked into how exponential growth happens. Okay. So that's why, I don't want to say that is the reason why there's any wealth inequality, but I will say that that is a contributing factor. Okay. So let's go and wrap this up. And again, you should be back in the Zoom meeting at this point. So we've just learned about this. Adding or subtracting a value to each data point will move the measures of position, and I list all of them there, but it does not affect the measures of spread. But multiplying and dividing each data point by a value, which is rescaling the data, will change the measures of position by the factor, and it will change your measures of spread by that factor. So this is one of those reference sheets. And if you look in the Canvas, do I still have the Canvas pulled up? I hope so. I do. So I just want to remind you that there are some references right here, Unit 2 reference posters. If you look at these, they have just a bunch of helpful things, and I actually stole that diagram from this. So this is a good resource to have available as you're going through, and you can see all this good stuff. Okay, and there's what we just looked at. Let me come back now. All right, a few more things to talk about. So, z-scores. We've been working with them already. When we find a z-score, we are actually shifting and rescaling the data. All right, so my data might live right here. I mean, it doesn't matter. Let's just pretend we have a distribution that lives right there. But I take z-scores of everything. And when I subtract the mean, what I'm doing is I'm taking this, the mean is right here, mean. But I want to now subtract the mean from everything. So every data point has the mean subtracted from the mean, or from it. And I end up with this being moved over. So now my data is sitting right here. And the very middle is going to be sitting right at 0. Okay, and then I'm going to divide by the standard deviation. What that does is it changes the spread of the distribution. So maybe this is very tightly clustered around the mean, but when I divide by the standard deviation, what it does is it flattens it out a bit. And now I get the normal distribution right here. So we are rescaling and shifting the data, transforming the data when we do z-scores. So subtracting shifts the data, and dividing rescales the data. And there we go. That's how we end up with a standardized normal model of 0 for the mean and 1 for the standard deviation. I'm not going to go into it any further, but your book has some more discussion on that, I think. Okay, so now if we look at this, suppose police set up a radar surveillance on the Stanford Street described in exercise 18. They handed out a large number of tickets to speeders going a mean of 28 miles per hour with standard deviation 2.4 miles per hour and a maximum of 33 miles per hour and an IQR of 3.2. Okay, great. Local law prescribes fines of $100 plus $10 per mile per hour over the 20 mile per hour speed limit. For example, a driver convicted of going 25 would be fined $150 based on that formula. Find the mean, maximum, standard deviation, and IQ are the potential fines. All right, so this is good. We got the mean, the max, the standard deviation, the IQR, and that's it. Okay, so here's what they are to begin with, just on the speeds that people go. So the mean is 28 miles per hour. The standard deviation is 2.4. I'm going to make sure I put the units here. The max is 33. and the IQR is 3.2. So we want to find the same sort of numbers, but we're basically transforming the data. We want to figure out the dollar amounts that people are going to pay on average. So if someone's going 28 miles per hour, then first of all, I need to kind of convert this into how many miles over the speed limit. And it looks like the speed limit is 20 on this street, because 25 would give you 5 going over. Oh, there it is. It says 20 mile per hour speed limit. I should read. Okay, so in this case, this person's speeding by 8 miles per hour. This person is speeding at the max by 13 miles per hour. Okay, so now I can do some conversions to this. All right, because this is a measure of position, both of these are measures of position, I can actually use this formula just to figure out what those are going to be. So $100 flat fee, which is what I'm adding to each data point, plus $10 times every mile per hour over, so this is times 8, gives me a new mean of $180. So on average, people who are caught speeding are paying $180 per ticket. Okay. So the max is 100 plus 13 times, 10 times 13, if I can do that right. So that's going to be 130 plus 100 is $230. So there we go. Now for the next two, these are measures of spread. Spread. Now my formula would say, so let me just do the standard deviation real quick. The formula would say do 100 plus 10 times the 2.4, except remember, for measures of spread, they aren't affected by adding and subtracting. So I want to ignore that part. My standard deviation, though, will be affected by multiplying. So it's going to be 10 times 2.4, which is $24. And therefore, the IQR, same thing. Now, I forget about the adding and subtracting. The measure of spread is not affected, but 10 times 3.2 is $32. All right. That is basically the takeaway. And we will see other things that get transformed later and how that affects different things. But the same idea kind of applies when it comes up later, all right? Without going too much into it, because it just sounds very vague. Last little bit to talk about is this right here, the normal probability plots. This is, I think, literally the last thing that they talk about before it moves into the problems. This is something that we're going to talk about it, introduce it now. We will not talk about it at all until we get to the very end, and we're going to talk about it one last time. Like, so we're going to introduce it here. It's going to be like one of the last things we talk about in Unit 12. But anyways, this is something that we can look at to figure out if the data, if it's appropriate to use a normal model. Okay, a normal probability plot compares the actual data points to an idealized normal distribution. So if the data is approximately normally distributed, you should see a straight line. And so what we do is, if we knew that we had 100 data points right here in the data set, we would say, okay, in a perfect normal model, where would those 100 data points fall? And there's math behind it, but we don't have to worry about it. So where would those data points fall? And we're going to compare them to our actual data points. And right here, you can see this is obviously skewed to the right. And so you can see that this gets a curve to it. So it didn't work out the way that we expected. Here, this is relatively normal, but it does have maybe outliers, or at the very least, some lower values. You can see, yeah, those don't quite fall in line exactly, but the rest of it's a straight line. Where we'd expect the data points to be, they tend to fall right where we expect them. Okay, so kind of the main takeaway is if you have a straight line, it's approximately normal, and that's good enough. All right, I don't need to mention that. Do make sure you're doing your homework. If you have any questions on submitting your homework, I have not seen how many people have been doing that, but if you have not been submitting your homework through Canvas for this unit, make sure that you're going back and doing it. And yeah, it's going to be that way moving forward. So this is kind of a review of all of chapter 6. And let's just run through it quickly. I think I only have like 3 problems here. In an approximately normal distribution with a mean of 100 and a standard deviation of 20, what proportion of data falls between 85 and 105? So it's always good to have a drawing of your normal model. And what we're saying is that a mean of 100 and the standard deviation of 20. So I know this is going to be 80 right here. This is going to be 120. So where's 85 and 105? Well, it's going to be about right here to about right here. So I want to figure out what that area is. What percent of the data is going to fall between that? So I need to get the z-score for 85. And I need to get a z-score for 105. Okay, and I have everything I need because 85 and 105 are my x's. And so I'll just say x sub 1, x sub 2. Anyways, I've got the mean and the standard deviation. So here we go. The z of the 85 data point is going to be 85 minus 100 divided by 20. And z of 105. I don't think I'm going to run through all of these. I'm going to let you guys kind of solve them and answer your own in a minute, but I'm just doing this one. 105 minus 100 divided by 20. So we can figure out what these z-scores are. 85, that's going to be negative 0.75 when we do that. You can confirm my math. That's going to be positive 0.25. And at this point, it's just a normal CDF calculation. So I'll let you guys do that part, and you can circle whatever answer is. Oh, we already have a circle coming up. I haven't done it yet, so I'm going to double check too.
Would you mind doing that CDF calculation?
Sure, I'll run through it. I'm just going to double check. All right, so for the normal CDF, when you go to, you hit second and your variables menu, and that takes you to distribution, and then normal CDF. So hopefully everyone's good on that front. We have now a lower and an upper bound. My lower bound is right here, negative 0.75 z-score. My upper bound is right here of 0.25 z-score. So on the actual calculator, it says lower, upper, mean, standard deviation. My lower is going to be negative 0.75. My upper is going to be 0.25. The mean and the standard deviation never change. And the only difference if you don't have the interface is that you don't plug it in like this. You just take those same 4 values and you put them in a row, negative 0.75, 0.25, 0, and 1 with your normal CDF.
All right, I got to run.
Okay.
Have a good day.
Thanks, you too. All right, so you guys are getting it right. It is about 37% of the data is going to fall there. All right, let me clear this real quick. There we go. So I'm just going to leave this question up there, and you guys can circle when you find the answer. And you might not have had enough time to work through this, but I'm assuming by now you're either close to finishing and you know what you're doing, or you got stuck somewhere along the way and you're waiting for some help. So let's just run through it. All right, we've got, because we know we're dealing with normal distribution and it's things related to a z-score calculation, I'm just going to write that down. Okay, and I'm just going to plug in what I know. So if I have a mean of 100, so I'm just going to plug that in, minus 100, a value of 70. This is my x. So I'll put 70. What is the standard deviation? So I know I'm solving for the standard deviation. It asked me that. So what I need to know, I know I need to find the z-score. Okay, and it tells me that it represents the 20th percentile. So in a normal distribution, wherever this happens to be, 20% of the data is going to fall below it. So what is this z-score? And the way we do that is inverse norm. So I want to do inverse norm. And I'm looking for the 20th percentile. So that's 0.2 with 0 and 1 is the mean and standard deviation. So we can navigate our way through that. And when I do the 0.2, I end up with a z-score of negative 0.8416.
What do you click on your calculator to pull that up?
That is the distributions menu, just like normal CDF. So you hit second and variables, second, and you'll see it's the
Okay.
third option.
Thanks.
Yeah.
Wait, where'd you get the 0.2 from?
The 0.2 comes from the fact that it's the 20th percentile. So that means 0.2 of the area falls below it.
Okay.
So yeah, and that's where it's helpful to remember 20th percentile means that this data point represents the spot where 20% of the data falls below it. All right, so if we've got 0.2 as the percentile rank and the area below that z-score, there you go. You got the negative 0.8416. So I'm just going to plug that in up here for this unknown z-score. Negative 0.8416. There, I do have some other practice problems for inverse norms. So if you guys are feeling confused about that, just hang out after class and we can go over some more inverse norm. They're the same ones we did on Friday, but it's been a 3-day weekend, so you might have forgotten. Anyways, now at this point, it's just an algebraic equation. You might have already gone through, and we do have the correct answer here. So I don't know if I'm going to, actually, the only thing I'm going to show you is that there is a trick right here you might already know of. If you've got a situation like this, you can just do a swap. And so basically your standard deviation is going to be negative 30 over negative 0.8416. And that's your calculation to get your 35.16. Okay, and that's just an algebra trick. That's enough on that one. Again, if you still have questions, something didn't click, just stick around. Let's make sure we get this all cleared up for everyone. Okay, this one maybe I'll run through because this is a problem from your textbook. It's not one that you had for homework, but I believe you'll have one like this tonight. All right. Agricultural scientists are working on developing an improved variety of Roma tomatoes. Marketing research indicates that customers are likely to bypass Romas that weigh less than 70 grams. The current variety of Roma plants produce fruit that averages 74 grams, but 11% of the tomatoes are too small. It is reasonable to assume that a normal model applies. That's good because we couldn't do any calculations otherwise. What is the standard deviation of the weights of the Roma now being grown? All right, so it's essentially the same question we just did. So we need to find, we already know the mean is, the mean is 74. 70 is this data point where people kind of reject anything less than that. So 70 minus 74 over the standard deviation gives us some kind of a z-score that works for the, well, what percentile? It's 11%. So apparently at the current average, the current distribution, it's the 11th percentile that represents the cutoff point where people don't buy those tomatoes anymore. So we need to find the z-score for 11%. And if I draw this, that's going to live somewhere right here. What's the z-score that everything falls underneath? So I'll do inverse norm. And this time my area is going to be 0.11. So again, on my calculator, it looks like this. Oops. There's no equals there, but it's 0.1101. And when I get my answer, it's negative 1.2265. So if you did that yourself, you can double check and see that that's right. Hopefully you agree. So I'm just going to plug that z-score in. Negative 1.2265 equals 70 minus 74 divided by the unknown standard deviation. I'll do my little switcheroo. So I get the standard deviation equals -4 divided by -1.2265. And that is going to be basically 3.26. Okay. Scientists hope to reduce the frequency of undersized tomatoes to no more than 4%. One way to accomplish this is to raise the average size of the fruit. If the standard deviation remains the same, what target mean should they have as a goal? I know a tomato is a fruit, but it is kind of weird to see that in a sentence. All right. The standard deviation remains the same. Our standard deviation will be 3.26. People are still going to reject it at 70 grams. So here's what we're doing now. We are trying to figure out what is our target mean. Now, we want a z-score for 4% because they're saying we only want 4% of these to be rejected. And that makes sense. People are going to reject it at 70. We don't know what the new mean is going to be, but we want to create a new mean. And we're going to have 3.26 as the standard deviation. So now, same thing as before, almost the same thing. So now I'm going to do an inverse norm. I need to figure out what this z-score is going to be. Now they're going to be rejecting it at a lower level. So here's my z-score for 4%. And they're not rejecting as much, but I still need to find out what that is. Inverse norm for 0.04, 0, and 1 gives me -1.7507. All right. And now we can do some algebra. I'm not going to show my work on this. If you have questions on what I just did there for part B of this problem, please stick around, make note of it, or speak up right now and we can talk about it. All right, the mean that I found is 75.7. I'll just round it to the hundredths, 0.71 grams. Okay. And the last thing right here for C. So I'll kind of put some separators here. This is part A. This is part B. So now let me separate this off. I'm going to do part C down here. Researchers produced a new variety with a mean weight of 75. Hey, that's good, which meets the 4% goal. What is the standard deviation of the weights of these new aromas? So it's almost the same question as before. Luckily, we already know the z-score for 4% because it said it meets the 4% goal. And now it's a 70 is the rejection weight. 75 is the new mean. And we've got a standard deviation, which we don't know. So I'm just going to copy the same z-score from before. -1.7507 equals basically -5 over the standard deviation. So if we go and solve this one, I get a standard deviation right here of 2.856 grams. There we go. Not much more to say about parts A, B, and C. Part D just says compare these two, well, I guess these produced by the two varieties. So we've got the new varieties. I don't know which varieties they're referring to. They might be referring to the original and the new one that has been produced. So the original had a mean of 74. The new one has a mean of 75. The old one had a standard deviation of 3.26. The new one has a standard deviation of 2.856. So we could say a lot of things. I'm not actually going to write anything out, but if this is an FRQ, you would. You could say the new variety has a higher mean weight and has less spread. So it's more consistent, more data clusters around the mean. So if you wanted to draw a diagram related to that, I'm running out of space. But for the old one, it'd be spread out a little more because the standard deviation is wider. The new one would have, this is an exaggeration, but you can see there'd be more clustering around the mean. Okay, I've kept you here long enough. But we covered the rest of chapter 6. And you don't need to worry about yesterday or Friday's homework, but today's, we've got these problems. You only need to submit one, but remember, run through all these homework problems until you feel like you understand it. All right, there's also Unit 2 FRQ practice that I believe is posted, and I will make sure that it is. I think it's still part of the same homework assignment. I'll double check to make sure that's there. Just like before, I believe one of those FRQs is going to appear on your test tomorrow, but that kind of goes away after a while. I don't give you the heads up after this test, I think. So if you have any questions, stick around. If you don't have any questions, have a wonderful day, and I will see you tomorrow. And don't forget, if you have questions on test day, you don't have to take the test right away, but that's it.